So the second topic of thermodynamics is a lot about like steam engines and pistons and Pivnert, ideal gas laws and stuff like that, and the three laws of thermodynamics, kind of putting all that together. It's a lot less mathy than the first topic of like rotational motion, but the concepts of thermodynamics is basically like Pivnert and how to apply the different processes and the laws of thermodynamics to do work for us, like steam engines and pistons and stuff like that. So let's go over the equations. If you notice, I didn't write them all up here because some of them aren't as useful as others. But these are the ones to know for sure and how to apply them. So the first equation is actually based off the first law of thermodynamics. If you remember, the first law of thermodynamics says that energy cannot be created or destroyed. It just simply changes from one form to the next. So whatever energy you start with has to equal the amount of energy you end up with. So here's an example of that. If I take a piston, for example, and I have some water in it, and I heat that water up and turn to steam, the water is going to do two things. First, the energy of the water is going to increase. All the molecules are going to increase their energy, move around faster, and they're going to increase internal energy. And then some of that water is going to turn to steam, and that steam is going to push the piston up, thus doing work for us. So the conservation of energy says the amount of energy we start with, which is heat. We put heat energy in, like MC delta T or ML, whatever. I guess it'd be MC delta T. We put heat energy in. That's our starting energy. And our ending energy was work. We moved the piston by doing work to it. It moved the piston, but first it had to increase the energy of the water. That's called internal energy, labeled as U. So conservation of energy says we started with heat energy. It heated the water, thus causing it to increase the molecule's energy, the internal energy, the U, and whatever was left, that's what did work for us. So the second law of thermodynamics says that, you know what, not all of that energy is useful. Only the work was useful for us in this case, because heating the water, that did nothing for us. Like this is internal energy, did nothing for us that was useful. The only useful part was work. So the second law of thermodynamics says that whenever you start with energy and you go and transfer to other types of energy, you're always going to dissipate energy. Another word for dissipate energy, in chemistry a lot, they use entropy, the disorder, disorganization. And the symbol for entropy is delta S. And that can be calculated with heat over temperature. We don't use that one a whole lot. I think a more useful one, pun intended, is the efficiency equation. Efficiency, N, is figured out by taking the useful energy, or work in this case, divided by your total. So if I wanted to find the efficiency of like a steam engine, I would just take the work divided by the Q. And it would be as like a percentage or a ratio, a decimal. Another equation for efficiency, which is kind of interesting that they figured this out. This is like the maximum efficiency that you could ever produce in a combustion system, like a Carnot cycle. They call it combustion system, Carnot cycle. The maximum efficiency you could ever produce can be figured out by taking, well, the efficiency is equal to 1, because that's the maximum it could ever be, theoretically, minus the cold temperature in Kelvin divided by the hot temperature in Kelvin. So here's what this means. Let's say I take this piston here, and the temperature inside is, the temperature outside is 300 Kelvin. The temperature inside is going to be hotter because it's heating up this stuff inside. So we'll say it's 600 Kelvin. 300 Kelvin is like a nice warm day outside. So 600 Kelvin, and that's really hot. So what's the efficiency of this system? Well, that's pretty straightforward. I would just plug it into this. The maximum efficiency that this system could ever reach, assuming it didn't dissipate energy to like the container or something, would be 1 minus T cold, which is 300, over 600 T hot, and my efficiency is 1 minus 0.5, which is 50%. So the best that this could do is 50%. If I wanted to increase the efficiency, I would try to have this ratio be smaller, have a smaller ratio there. So to try to better my efficiency. Then remember the third law of thermodynamics kind of applies to all of these. We don't do any calculations with it, but we basically say third law of thermodynamics is this. Absolute zero is 0 Kelvin. The motion of molecules is dependent on the temperature. So temperature is proportional to the motion of molecules. And so as molecules heat up, they move faster. That's the third law of thermodynamics. So the higher the temperature, the faster the molecules move. Another way to think of it is that temperature is proportional to the average kinetic energy of the molecules. Kinetic energy, E1/2 mv squared. So the faster the molecules are moving in that substance, the higher the temperature is going to be. Not really any calculations with that, just the concept applies. It. It's kind of based off internal energy. If you looked at the equation internal energy, there's a temperature perspective of that. There 3 has nRT. So as temperature goes up, the energy goes up. Okay, so those are our 3 laws of thermodynamics. Energy cannot be created or destroyed. There's only, second law, there's dissipated energy, meaning that only some of it's useful. Third law, moving particles, the faster they move, the higher energy they are, the higher the temperature. Now, there's one more equation that's useful in that packet, and there's one more I'm going to add to the packet because I think you should just know it, and it's because it's going to help make things simpler. And that last equation is work equals pressure times volume. And here's actually where it comes from. Here's where it comes from. So I'm going to move this out of the way for a second. So if you remember, work, oh my gosh, work was essentially force times distance, and pressure was force over area. And volume, if I want to find the volume of something, I could take this distance, the height essentially, times the area. If I take the area of this and times it by the distance, then I find volume. So volume is area times distance. So if I put those 3 equations together, let's see. Force would be pressure times area. And area times distance is volume. So that's where the equation comes from. So pressure times volume is also another equation for work. Now, a lot of times in thermodynamics, they use PV diagrams or PV graphs, so pressure versus volume graphs, as things are changing. So if I increase the pressure of something, how does the volume change? If I increase the volume of something, how does the pressure change, etc. And we can either use this equation or look at the graph. And the area that the graph, the shape of the graph makes, and we'll do an example, that's going to be the amount of work that was accomplished by that piston or steam engine, whatever it is that we're changing the pressure and volume of. So let's go over the 4 types of processes for thermodynamics, and then we'll go over a couple examples to kind of tie everything together. So, the first type of process is an isothermal process. Now, these are not in any order. Isothermal process is one of the 4 types. Iso means constant or same, meaning you keep the same. Thermal means temperature. So this is a process that maintains the same temperature. So an example of that is if I take like a basketball and I inflate it, I pump it full of air. The temperature of the ball doesn't change, but what does change? The pressure is increasing and the volume is increasing. So the pressure and volume are increasing, so I know those things are changing, but the temperature of the ball really doesn't change. It may be a little bit, but not too much. So same temperature, that's an isothermal process. Isovolumetric would mean it has the same volume, meaning that the volume doesn't change. So here's an example of that. Let's say I had a container like this, a glass container, so it can't change the volume, it's like fixed, it's solid. And I start pumping some air into it. It's getting harder and harder, the pressure is definitely increasing. Now the temperature might change, the temperature's going to be changing a little bit. You can probably measure it. Actually, I can actually get some alcohol to boil if I put alcohol in there. I can actually get the alcohol to boil. So the temperature is increasing, the pressure is increasing, but the volume is not changing. So isovolumetric means it has the same volume. It doesn't change volume. Isobaric, bar is a measure of pressure. So this has the same pressure. So here's an example of that. this example here. Now, isobaric is usually pretty hard to find in real life, a perfect scenario, but you can get pretty close. So let's look at this. If I take this container and I heat this water, the first thing that's going to happen is the water is going to heat up. Then it's going to turn to steam. The pressure is going to increase and raise this piston up, and the pressure is going to decrease again, so it maintains the pressure. So it increases the pressure a little bit, but then it decreases the pressure a little bit to kind of maintain it. So that's isobaric because the pressure is basically maintaining itself over time. So that's an isobaric process. You heat something up or cool something down, and you allow that to expand or compress, get smaller or larger. Adiabatic is where multiple things are changing. So you can kind of here's the equation that I would add to your list of equations. P1 V1 over N1 T1 equals P2 V2 over N2. This is like putting the Pivnerd equation into full gear. Like if something is isobaric, that means that P1 and P2 are exactly the same number. If something is isothermal, that means that V1 and V2 are the same number. If something is isothermal, that means T1 and T2 are the same number. If something's adiabatic, that means that all these things are changing. Adiabatic is something that, it's very efficient. It's very powerful. It's trying to change all these things really quickly so that no heat is lost. So actually, the thing that's not changing is heat. So like the internal combustion engine, something happens really fast, boom. You're changing the pressure, you're changing the temperature, you're changing the volume all at once. So all these things are changing really quickly, and that can produce a lot of power. So adiabatic is very powerful because it happens really quickly, or you have things really well insulated so that heat can't leave, and you want things to maintain, the heat to maintain, and everything else is changing rapidly. So let's go through a couple examples, and then also talk about like how do we do some pressure volume diagrams to kind of tie all this together. All right, so let's say we have this exact piston again. So we're heating it up, and the pressure is constant. We keep the pressure constant of 120 kPa. It stands for kilopascals. And the initial volume of the container is 0.05 cubic meters. So that's, yay big, And then it doubles in volume to 0.1 cubic meters because we're heating it up, so the gas is going to expand and heat up. And to do that, we have to put heat in of 1 times 10 to the 4th joules. So that's 10,000 joules of heat. So we put heat in, it expands. So we're going to answer some questions here. A, let's sketch a PV diagram. Let's sketch what the pressure volume looks like. Well, let's think about it. We need to basically plot 2 points on this diagram and then connect them. So V1 is 0.05, so it's not 0. So let's just put V1 at like 0.05. So let's say 0.05 is right here. And V2 is 0.1. Okay, so we know it starts at 0.05 and goes to 0.1. Then, let's see, the pressure is 120,000. So we'll just put 120,000, because kilopascals is 1,000. 120,000. It starts at 120,000, and it starts at 0.05, and it ends at 120,000, ends at 0.1. Now, diagrams are always represented with arrows. So we started here, and we ended there. So that's our diagram. It's the graph, but we have an arrow showing which direction it went. We could have done the other way, and the arrow would have went the other way. Now, the diagram is done. B, which process is this? The process, now we have 4 choices here. Is it isothermal? No, because we're adding, the temperature is obviously increasing, so it's not going to be isothermal. Is it isovolumetric? No, because the volume changed. Is it adiabatic? Maybe, but is it isobaric? Yes, because it even tells us the pressure is constant. The pressure stayed the same. So it is isobaric. That's what you do, is you kind of go through like saying, what thing is not changing? If the temperature stayed the same, then you know it's isothermal. If the volume stays the same, then the graph, if the volume stays the same, the graph's going to be just a vertical line, either up or down arrow, depending on which way it went. Isobaric is going to be a horizontal line, and then isothermal is going to be a curve because they're both changing. It's like 1 over x. Adiabatic is also going to be a curve of some sort, but it's going to be a much steeper curve because things are happening really fast. So it's going to be really steep. It's very powerful. So it's going to be steeper than that curve. So those are the that's the different diagrams that you'll see. Either vertical, horizontal, or a curve. A steep curve or a shallower curve. So which process is it? Well, it's isobaric because the temperature, pressure stayed the same. How get the work done? So here's the equation for work. Work is pressure times the change in volume. Or another way to think of it, it's the area of the PV diagram. It's the amount of area, if I were to take a shape, and I use the axis as one of the lines of the shape, connect the dots, I need to find the area of this shape here. And that's how much work was done. Now, the area is going to be the change in volume, 0.05, times the pressure. So it ends up working. Ends up working. So 0.05 times 120,000. I should be able to do this in my head, but I can't. I think it's 6,000, but 120,000 times 0.05. 6,000! Yeah, so 6,000 joules is the work. Now, just for a side step, let's say we had a graph that looked like this. To find the area, you would have to either know calculus to find the area of that shape, or you can approximate that as like a triangle or a trapezoid or something and get the area of that. Another example, let's say I had a PV diagram, and say I went through multiple steps. So first I went through like a isobaric step, then it went through an isovolumetric step, then it went back to an isobaric step the other way, then it kind of went back to where it started. I would find the area of that shape then. So I'd find the area of that rectangle. And that'd be my work done. So one way, a PV diagram really helps make things simpler because it visually shows you what's happening. It's a graph. And all you have to do to find the work is just find the area of the shape that it makes. Or you can use work times change in pressure, but sometimes you don't have those numbers. You have to look at a graph, or you have to approximate them. Because this is an approximation where the graph is always going to be 100% right. Let's calculate the efficiency. Well, efficiency is my useful over total. Well, my useful was, if I do this right, 120, 123 times 0.05, 6,000. This was my useful. That's my work is useful. I want to accomplish something, I did work. So 6,000 was my useful. So efficiency is useful over total. How much energy did I put in? My heat. That's what I put in. I heated it up with 10,000. 1 times 10 to the fourth. So 6,000 over 10,000 is 0.6. So my efficiency would be 0.6 or 60%. Both are acceptable answers. Finally, calculate the change in internal energy. That's basically saying how much energy, if this was water, how much energy did the water absorb before it actually turned to steam? Well, we're looking for you. I'm looking for you. And we could just use that first equation. We know that we put in 10,000. We got 6,000 useful. So my change in internal energy, how much the water's energy changed, is got to be 4,000. So 40% of the energy went into the water. The other 60% went into actually the steam gas, which pushed the piston. So there's thermodynamics in the process. Like, we went through the diagrams, which will be very popular. You're going to see a lot of diagrams with a unit. But then the equations are pretty straightforward then. Like, just understanding the diagrams, Pivnert, like the ideal gas laws, pressure, volume, moles, temperature, how they affect each other. And then the 3 laws of thermodynamics, especially the first 2. Energy cannot be created or destroyed. And then there's an efficiency factor of number 2, like just dissipated energy.